statics is so nice because what makes something static? It means it's not moving. So when we're looking at statics, we're talking about a stationary object, for example, a hanging a hanging sign. But of course, there's still forces at work. We still are in dynamics, so we want to look look at what kind of forces are happening. But what's really nice is even if there's forces at work to make an object stationary, my acceleration is always going to be 0, which is so wonderful, because then my net force is equal to 0 in the x and y direction, and it does make life just a little bit easier when we can say that. So that's what's really nice about statics, is that things are not moving, so ma is 0, net force is 0, and it makes things just a teensy bit easier, which is really nice. So that's what we're going to do today. We're taking a break from dynamics, which is when objects are accelerating, and we're going to do some static objects, i.e. ones that are not accelerating, they're not moving, they are just staying in place, but they need forces in order to do so. So hanging signs are a really great example of that. So here we go. We have a sign hanging as shown. Okay, so we have rope A and B here. Rope A has tension of 200 newtons on it. We want to know what is the tension in rope B. Okay, so again, this guy here has 200 newtons. So I'm going to go ahead and draw a free body diagram just a little bit aside from this. Okay, so here's my sign. Okay. Again, what are all the forces at work here? Well, we have the 2 ropes. So we have the rope that's kind of going like this. Okay, so I'm going to call that's A. So that's the force of tension in rope A. And then the tension in rope B is going to the right here. So force of tension in rope B. And that's what we're looking for. So we're looking at going, how the heck are we going to find that? Well, first of all, let's finish drawing all the forces at work, because we know what else. Gravity is going downwards. And then A is at this weird angle. So we need to break that into the x and y directions. So here's the force of tension in A in the x direction, and then in the y direction. Okay, so we're ready for all these subscripts. That's force of tension for A in the x direction. Here's a force of tension for A in the y direction. It's a fun thing. All right, we know that this angle up here is 30 degrees, so I better know that. Okay, so we're going to go ahead and find force of tension for B. So here's the thing, is B is just in the x direction. So that's nice. So I know if I set up my sum of forces in the x direction, I should be able to kind of find that, okay? So let's see if we can just go right to that. So part A, I'm just going to I'm trying to find force of tension in B. In this case, since nothing's accelerating, doesn't matter which way you define as positive, either way. So I'm just going to go for the right. And I'm saying, okay, my sum of forces in the x direction is equal to mass times acceleration. Oh, but there's none of that, so that's 0, yay. Okay, so what are forces am I summing? So I have force of tension in B is just all in the x direction, so I don't have to even say that it's in the x direction. And then from that, I'm going to subtract force of tension in A, but in the x direction, and that equals 0. Can I get force of tension of A in the x direction? Well, remember, I do actually have the force of tension in A. It is 200 newtons, right? So therefore, yeah, I absolutely can. This is a 30-degree angle right there. So F of the force of tension in the x direction is on the opposite side of that 30-degree angle. So I can take 200, multiply it by sine of 30. There you go. If you want to use the 60-degree angle, you absolutely could. You'd then multiply by cosine of 60 instead. So actually, look at that. Force of tension in the A direction is force of tension of A times sine of the angle of the 30-degree angle. So look at that. Force of tension in B actually isn't so bad. That's just 200 newtons times sine of 30. And that gets us 100 newtons. Woohoo! So again, we have two vectors in the x direction, force of tension in B, force of tension of A in the x direction. So it makes sense that they'd be equal and opposite because we know acceleration is 0 and my net force in every direction should just be 0. So that's what makes statics so much nicer. Let's go over part B. What is the maximum mass of the sign? So basically, if your ropes have this much tension in it, then how much mass could this have? How much mass would produce that amount of tension? And then, of course, if it was heavier than that, it would need more tension, and then maybe it would break. So let's figure out the mass of this sign. Ack! I don't want this at all. There we go. So mass, I'm probably going to have to go over to the y direction because we know mass is part of Fg, right? Because that's mg. So that's probably what I got to do. Okay, so again, does not matter whatsoever which direction I say is positive. I'm going to go ahead and say downwards is positive because I can. Okay, sum of forces in the y direction equals mass times acceleration in the y direction, which is 0. So, okay, force of gravity then is positive. I'm going to subtract force of tension of A in the y direction. Oh boy. And that's going to equal to 0. Okay, so Fg is mg. This equals force of tension of A in the y direction, which is just force of tension of A times cosine of that 30-degree angle, because of course that's on the adjacent side now. And then we're looking for G. So M. So what do we do here? We divide both sides by G. And that's what we got to do. I'm not going to show that step because I'm running out of room. So force of tension of A was 200 newtons. Okay, I'm going to multiply that by cosine of 30 degrees. That gets me the y direction. And of course, what I'd have to do to get m all by itself is divide by g, which is 9.81 meters per second squared. And I get a mass of, I'm running out of room here, 17.7 kilograms. Okay, so statics really, when you compare it to what we just did with inclines, it's really not that bad, is it? It's not that bad at all. So just remember, you always need to break things into their x and y directions if something is at an angle. But the nice thing is here, our net forces are always going to equal to 0. So, really awesome. Let's do another example. Here now we have 2 ropes, okay, or 2 cables holding up a sign. So again, let's draw our free body diagram. Oh. So there's our sign. So we have 2 cables here holding it up. So there will be tension in both of those. Okay. So that's force of tension there. Okay, they're both at 41-degree angles here. So just a little bit of a math trick. That's actually the same as this angle. Imagine that. So there we go. When we break this into our x and y directions, we have our 41-degree angle right there. And same thing for this guy. Okay. They are probably, since they have the same angle, they probably are have the same tension, but just in case, I'm going to call this A and this guy B. Okay? And then, of course, we do need to, again, make sure we have stuff in the x direction and the y direction as well. So remember that our angles are right there, so our y direction should be multiplying by sine of that angle. And our x direction should be multiplying by the cosine of that angle. But the biggest difference here is that they're just in opposite directions. So our x's are in opposite directions, but the y's are the same. Okay, we're missing one force, and that is our force of gravity, of course. So there we go. We got that. So now I want to know what is the tension in each cable. So I'm looking for the tension in A and the tension in B. It's probably the same. But before I just assume that, I actually have to prove it. How do I prove it? Well, let's look at forces of tension in the x direction. Okay, again, I can make any direction I want positive. So since I put A on the left, I'm just going to say left is positive because, well, I just want it to work out that way. All right, and that should equal to mass times acceleration, which is, of course, 0. See, don't you love statics already? Okay, so what does this mean? That means that the force of tension in A in the x direction minus the force of tension in B in the x direction should equal to 0, because those are my only two forces in the x direction. How do we have force of tension of A in the x direction? I have to multiply it by cosine of the angle, which is 41. So force of tension in A times cosine of theta, and then I'm going to add ft for x, bx into the other side, and that should be force of tension in the rope B. And again, this will be times cosine of the angle because it is the adjacent side. Okay, so another thing that's important to note about both those angles is that they are the same. Why is that really important to note? Because what happens in the next step when you're like, okay, well, let's try to solve for force of tension for A. You divide by cosine of theta. And then anything you do to one side, you got to do the other. But then something weird happens. Look at that. They just cancel right out. Of course, if that wasn't a 41-degree angle, we couldn't cancel them out. So obviously can only do that when it is a 40-degree angle or 41-degree angle and when it's the same angle. But it is here. So we just proved, oh yeah, force of tension in A is in fact equal to the force of tension in B. Good. So now if I just find one of them, I can find the other. Or really, as long as I know that they're kind of, well, here they're not even equal and opposite. Now they're both going upwards for the y direction. So instead of saying force of tension in A in the y plus force of tension in B in the y, I can just take one of those and multiply it by 2. Because they're the same thing. Isn't that so nice? Okay, so let's go over to the y direction and see if we can work out what the force of tension is here. Okay, so here I'm saying, going to make sum the forces in the y direction, which should equal to mass times acceleration, which is, of course, 0. Okay, so how do we do this? We have the force of tension of A in the y direction plus force of tension of B in the y direction. Why am I adding them? Because they're both upwards. But then I have to subtract the force of gravity, and that should equal to 0. Okay, so let's break this down just a little bit more. So how do we get the y direction here? Well, those are on the opposite sides of the triangle here. So I'm going to multiply by sine of theta. So this is force of tension in A, sine theta. Although I don't even need to say it's the force of tension in A anymore. It's just the force of tension in the rope, because they're the kind of one and the same here. Times force of tension times sine theta. And I can add FG to both sides. So I'm going to do that. And I get MG over there. So here, what do we have? We have the same thing plus the same thing. We have something adding to itself. Easier way of saying that is just 2 times that thing. Right? That's what happens when you add something to itself. And that makes it so much easier because then we just have FT in one place instead of like this where it's in 2 places. And that's just a little bit of a mess. Okay? So that does make our life pretty nice. It makes it quite a bit easier. So now that I have that, I can solve for the force of tension, which of course is just going to be the same for both of them. So we should have mg divided by 2 times sine of that 41-degree angle. Okay. So mass, what was it again? 25 kilograms times 9.81 meters per second squared divided by 2 times sine of 41 degrees. Okay. And the force of tension we get is 187 newtons. Okay, so there we go. So, that's not bad, right? We can do that when the angles are the same. All right, so of course I got to do one more thing to you just to make it a little bit more difficult because, well, that's physics. I'm sorry. What if I don't have the same angles here? So here's an example with two different angles. And yes, it is going to complicate things quite a bit more, but that's okay. We're physics students. We can do this. So we have the diagram here. We have the mass of the traffic light is 37.1 kilograms. Great. And determine the tension in each cable. So basically I have no information. But we do have the angles as well. So don't forget about those. So first step, when in doubt, just draw a free body diagram, because sometimes you just don't know what else to do, right? And so we have this guy with this tension kind of going all the way out here. That's cable B, so that's force of tension for B. This guy has a cable kind of going like that. So that's force of tension for A. Probably shouldn't be going higher than the other one. Okay, so there's force of tension for A. Okay, so I have these angles up here, so I'm going to draw them so I can keep those angles in there. So there we go, there's that 50-degree angle. So I'm going to call that theta A. And then again, I want to draw my triangles like this, because of course, anytime you have this, you got to make sure you draw your X and Y directions. And here's my angle there, so I'm going to call that theta B. So I'm going to make sure that I have them labeled differently this time, since they are different angles. Okay, and then I have one more thing here, and that is the force of gravity going downwards. Okay, yikes, where do you even start when you're looking for the force of tension? Well, when you don't know where to start, just start in one direction and go until you can't, and then go to the other direction. So it doesn't matter, again, which I say is positive, A or B, or left or right, because there's no acceleration here. Okay, so I went ahead and said left is positive. So we're going to start with the X direction here, if you couldn't tell by making left positive. Okay, and of course that's 0. So what are my forces in the X direction? Well, I have the force of tension in A in the X direction. And then from that, I'm going to subtract the force of tension of B in the X direction, because of course one is going to the left and one is going to the right. So I do need to subtract those, and that should equal to 0. Okay, so again, we can break this down a little bit further. So force of tension of A in the X direction and force of tension of B in the X direction are both my adjacent sides in each of these triangles. So I need to multiply them by cosine, but in this case I just have to make sure that I know one has a cosine of theta A and one has cosine of theta B. So I'm going to go ahead and, if you added that to the other side, then you get this. Okay, so that's what we have here. So I want the tension in each cable. So what if I did want to find the tension in cable A here? What would I do? I divide both sides by cosine theta A. So I do this, and I do this, and divide by cosine theta A, and there we go. I'd have it, except for there's a problem here. What's the problem? I don't have force of tension in B. So this is what I'm saying. Go until you're stuck, and then go to the other direction, because sometimes you just can't do anything. Okay, so I'm going to go over the Y direction, and I'm actually going to do that on another page. So Y direction, I'm going to go ahead and say upwards is positive. I'm going to sum all my forces in the Y direction. And that should equal to mass times acceleration in the Y direction, which is 0. Yay! So forces in the Y direction. Let's go back here and look. So I have my tensions both for A and B. Oh my goodness. And those are both going upwards. So those will be positive, and then FG is going downward. So obviously I'm going to subtract that. So I have the force of tension in A in the Y direction plus force of tension in B in the Y direction minus force of gravity. And that equals to 0. Okay, let's try to keep going here, because we can, I guess, maybe. We'll see. So again, I can force of tension in the y direction of A and B. I can break that down a little bit more. They're both on the opposite sides of the triangle, so therefore I can multiply them by sine of theta. So force of tension of A times sine of theta plus force of tension of B times, sine of theta of A times sine of theta B. We've got to make sure that we keep those straight. And if I add FG to both sides, then I'll move over here. And we know it's mg. So, okay. I'm stuck again. I have mass. I have the angles. But again, I still have two unknowns. I don't know that, and I don't know this. Okay, so if you're stuck here, that's okay. You've already done a lot of work. And let me help you out and tell you what to do. Because at this point, you just can't really solve for anything easily at this point. Okay, so here's what you're going to do. We actually came up with this lovely little expression of what force of tension in A looks like. Okay, unfortunately, it's not a little expression. It is a little bit more complicated. But why does that help us? Well, it's in terms of force of tension in B. So I'm going to say if we substitute that in for force of tension in A in my other equation that I just had, I will no longer have two unknowns. I'll have only one unknown. It'll just be in two places, and so it'll be really, really annoying. Okay, so again, this force of tension of A equals force of tension in B times cosine theta B divided by cosine theta A. So remember, we found that. And now I'm going to substitute it in to this guy right there. Doesn't that sound like fun? So remember, what did we find? We found force of tension in A is equal to force of tension in B times cosine of the angle at B divided by the cosine of the angle at A, right? Yeah, that's what we found. So again, I'm substituting this in for force of tension in A because this equal sign here means that these two things are equal. So for force of tension in A, in there, I am going to write, instead of force of tension in A, I'm going to write force of tension in B times cosine of the angle at B divided by cosine of the angle at A. And then force of tension of AI multiplied by sine of the angle at A. Oh boy. And then, what did we do? And then we add force of tension at B times sine of theta B equals mg. That's just kind of rewriting it. Okay, doesn't that look like a fun equation to solve for? Okay, so the good news is we only have one unknown now. I know angle at B and the angle at A and angle at A and the angle at B. I know mass, I know gravitational acceleration. I just don't know force of tension in B. So I'm going to have to solve for that, and that's a little bit of a mess. So we're going to use a few tricks here first. We're going to use this math trick that I just showed you in the last video. And that is that sine of theta divided by cosine of theta of the same angle is equal to what? Tan of theta. You're going, you're not dividing those? Yeah, you are, because you're multiplying this whole fraction by sine, and then that basically just means you multiply it by the numerator. And then you have sine theta A over cosine theta A. So that's tan theta A. Can't do anything with cos theta B, though, because that's a different angle. It's the angle at B, not the angle at A. Okay, so even though you're like, how did that make anything any easier? Just trust me. I promise it did, okay? Because then we have this times cosine theta B plus, not sine, tan of the theta at A. Tan theta A. Plus force of tension at B times sine theta B equals mg. And you're going, Miss Waters, I still don't see how this is any simpler. Here it is. Now, it's at least we don't have brackets and that big mess up there. Look, we have on the left side of the equal sign two big terms, right? There's one term and there's another. And guess what is a factor in both those terms? Force of tension in B. So guess what? I can factor it out because it's a factor in both terms. So what happens when I do that? Something magical. I can solve for the force of tension in cable B because I factored it out, right? What's left here is the cosine theta B times tan theta A plus the sine of theta B, and that is with the FTB factored out. And now I can solve for FT, the force of tension at B, by just dividing it by everything in the brackets, right? So that's what I'm going to do. And then, of course, I got to divide that side by the same thing. I'm not going to write it out. I'm sorry, you guys. It's too much work, and you don't have to do it. I don't need to see that step. So force of tension at B is equal to mg all divided by cosine of the angle at B times the tan of the angle at A plus the sine of the angle at B. Oh my good Lord. That's a lot of work. Okay. So now we actually have to just remember what all the things were. So the mass of this was 37.1 kilograms. 0.1 kilograms. G, of course, I know is 9.81 meters per second squared. Divided by, okay, and now I have to figure out what these angles were. So the angle for B is 30 and the angle for A is 50. So remember that. So cosine of 30 degrees, because that was the angle at B, times the tan of 50 degrees. Okay, and then plus the sine of theta B, so that's 30 degrees. Oh my goodness, that sounds like a fun thing to type in your calculator, doesn't it? So here's my tip, is I would do actually the denominator first. I would say bracket cosine of 30 times tan of 50. Remember to close the individual brackets just for the angles that you put in. And then plus sine of 30, and then I would just get that answer. And then I would go bracket 37.1 times 9.81, and the bracket divided by your previous answer. And if you do that, you should get 238 newtons. Okay? So again, I would try that on your calculator because that is a difficult thing to type into your calculator, and it sucks to do all that work and get it wrong just because you didn't type it into your calculator right. Are we done? We found the force of tension in B. What does the question say? Determine the tension in each cable. So that's annoying. But hey, wait, I just found the force of tension in B, which goes right there. And then I already have an equation for force of tension of A and what it equals. And it's in terms of like two other angles that, I know those angles. Oh my goodness. So I can now actually find force of tension in A, because I already have like a whole equation set up for it and everything. So please don't forget to not round that 238 when you're using it in here. So that's actually 238 newtons because it's the force of tension of B times cosine of the angle at B, which is 30 degrees, divided by the cosine of the angle at A, which is 50 degrees. Okay, and then I can pretty easily find the force of tension at A because I already had that nice equation all set up for me. And it's 320 newtons. Okay, so yes, up until there, statics was pretty nice, but now it's a big old mess. So yeah, but hey, that's physics. It's a lot of rearranging. It's a lot of mixing equations together to get a new equation. And no one said it was easy. I actually did warn you that it's very, very difficult. So go practice, and good luck.